welcome to this explainer. Look, if you're a product manager, a builder, or honestly just someone who is completely exhausted by the mainstream media's surface-level coverage of artificial intelligence, you have landed in exactly the right place. Our goal today is simple, but it's ambitious. We are moving way past that basic 6th grade understanding of AI, and we're going to build a 12th grade first principles foundation. We're going to get under the hood and look at the actual physical hardware that makes this entire AI revolution possible. So get ready to completely transform your understanding and ultimately your products.
Okay, let's dive right into this. Can machines actually think? It's a question that has haunted and inspired researchers for absolutely decades. The whole story of AI actually begins with an attempt to just replicate the human brain, and it starts with Alan Turing. Back in 1950, Turing, who you probably know from the Hollywood movie The Imitation Game, published a genuinely groundbreaking paper called Computing Machinery and Intelligence. In it, he proposed a test where a human interrogator tries to distinguish between a human and a computer based solely on their answers. Passing this test, that became the ultimate benchmark, and it sparked this incredible, relentless quest to build a machine that could literally mimic human thought. So, let's briefly trace how that huge philosophical goal became the modern reality we live in today. We start way back in 1950 with Turing's proposed test, which set our foundational goal. Then, we fast forward through decades of really quiet, behind-the-scenes research, leading up to a crucial turning point around 2024. That's when the essential AI blueprints for smart builders really started coming together. And that sets the stage perfectly for 2026, the absolute explosion of the modern AI hardware boom. It's crazy to think about, but Turing's early theories directly laid the groundwork for the massive physical AI infrastructure that we rely on every single day.
So, here's our roadmap for today. First, replicating the human brain. Second, the language of computers. Third, specialized processing units. And finally, the titans of AI. We are going to completely demystify all this dense hardware terminology by taking a highly structured micro-to-macro journey.
Section 1. Replicating the human brain, the biological baseline.
Before we can even begin to understand artificial intelligence, we have to understand the ultimate benchmark it's trying to copy, how your own biological brain processes information. It's happening right now in your head as you listen to my voice. Let's walk through exactly how that works. Step 1. Visual and audio stimuli, like watching a human face talking, enter your eyes and ears. Step 2, your body acts as this incredible biological converter, instantly translating those sights and sounds into electrical signals. And Step 3, those signals travel straight to your brain, where neurons communicate across various departments and fire together. That simultaneous activation is exactly what allows your brain to interpret the inputs as specific words and images. For AI researchers, this third step, what's happening inside the brain, is the holy grail.
And this brilliantly illustrates the core equation of this whole explainer. Fundamentally, the human brain is just a combination of biological circuitry and logic, which allows it to process massive amounts of information in real time. Artificial intelligence is simply humanity's best attempt to replicate that exact equation. But instead of biological circuitry, AI uses electrical circuitry. And instead of biological logic, AI uses artificial neural networks.
Which brings us to Section 2. The language of computers, the microscopic foundation.
If the brain equals circuitry plus logic, then to build AI, humans absolutely have to master electrical circuitry. And that starts by zooming all the way down to the microscopic, atomic-level building blocks. Everything starts here, with the transistor. By definition, a transistor is a semiconductor device that uses electrical signals to switch between two states, off and on. That's literally it. That is the native language of computers, binary. By simply applying a tiny voltage, these microscopic devices switch off and on, creating the fundamental 0 and 1 foundation for every complex operation a computer will ever perform.
Now let's put this into perspective and look at how these tiny binary switches scale up. When you string just 8 transistors together, you get 1 byte. Scale that up to 1,000 bytes and you have a kilobyte. 1 million is a megabyte. 1 billion is a gigabyte. So the next time you're checking your phone storage or buying a cloud data plan, keep this scale in mind. Those everyday terms, megabytes, gigabytes, they aren't just abstract digital ideas in the cloud. They literally represent millions and billions of microscopic physical transistors switching on and off in the real world.
But here's the thing. Just having billions of transistors isn't enough. They have to be highly organized. Enter the core. Even using last-generation 7-nanometer technology, engineers somehow managed to pack billions of transistors into a space of just 1 to 2 square millimeters to create a single core. In the past, a single core processed tasks sequentially, one after another. But today, processors are organized into multiple cores, which allows them to execute massive amounts of tasks in parallel at the exact same time. This massive shift from sequential to parallel processing, that is the key to unlocking AI.
Let's move into Section 3, Specialized Processing Units, the processing powerhouses.
Now that we understand microscopic cores, let's zoom out a bit because this gets really exciting. We're going to see how these cores are bundled together to create the specialized processing engines we interact with every day. Just take a look at this jaw-dropping number, 92 billion. Let that sink in for a second. Apple's latest M3 Max chip houses a staggering 92 billion transistors. The sheer density and engineering required to manufacture a physical object with 92 billion moving microscopic parts is absolutely awe-inspiring, and it sets the stage for how these parts are brilliantly delegated to handle different tasks.
To truly grasp how those billions of transistors are used, let's break down Apple's silicon. Think of this kind of like explaining the parts of a high-performance car engine to a friend. First up, you have the CPU. Its original purpose was just to be the main brain of the computer, and it totally excels in low-latency processing, basically handling general, everyday logic. Then you have the GPU. Originally, this was designed purely for rendering 3D graphics, but its architecture features incredibly efficient cores that work in parallel, which, as it turns out, is perfectly suited for the sheer parallel processing muscle needed for AI workloads. Finally, we have the neural engine. This wasn't in original computers at all. It was designed from scratch entirely for the millions of parallel calculations demanded by today's advanced neural networks.
And finally, Section 4, the Titans of AI, powering the future.
So, we've gone from the tiny microscopic transistor all the way to bundled processors. Now it's time to look at the macroeconomic reality and the massive, unbelievable scale at which this circuitry is currently being deployed by the biggest companies on Earth. Now, what's really interesting about this slide is the sheer scale of the hardware powering today's most advanced AI. If you want to run high-end models like GPT-4, you absolutely need NVIDIA's CUDA architecture, and that relies on thousands of these, the NVIDIA H100. Look at these specs. A single H100 boasts 80 billion transistors, 112 CPU cores, 528 highly specialized tensor cores, and almost 17,000 CUDA cores. It is just an absolute monster of specialized architecture.
But, as you might guess, all that highly specialized power comes with a genuinely staggering price tag, $73,000. That is the cost of just one single NVIDIA H100. And because the demand from builders and tech giants is so astronomical right now, you can't just casually go online and buy one. You have to pay that massive premium and still join a huge waitlist. That is the incredible cost of entry in the modern AI boom.
Of course, NVIDIA isn't the only major player in town. Beyond Apple and NVIDIA, we also have Google's TPU or Tensor Processing Unit. Google created these specialized processors specifically for dense matrix operations using their own TensorFlow software. It's another brilliant example of how hardware is currently being custom-built from the ground up to perfectly match the incredibly specific demands of AI software. It really cements the incredible advances we've made in physical circuitry.
So let's bring this all together. We started today by looking at the human brain, biological circuitry plus logic. We've just seen how humans have completely mastered electrical circuitry, packing billions of transistors into microscopic spaces to create highly specialized processors at an unbelievable cost. Which leaves us with this final, really provocative question. What happens when this massive, unfathomable electrical circuitry finally unlocks advanced computer logic? The physical hardware is already here. The foundation is absolutely set. The real question is, how will all this physical hardware ultimately power the neural networks and large language models that you are going to build with tomorrow? Thanks so much for joining me for this explainer, and I truly hope this helps you go out and build something incredible.